Hello everyone. In today's presentation, we'll discuss few problems on Module 3. In Module 3, what we discussed already in the regular presentations, what we were earlier considered, we saw about the impulse response properties, and based on the properties, we solve some of the problems. Unit step response for impulse functions, and also we saw about Fourier series, continuous time Fourier series signals and its calculation of Fourier series coefficient, and the vice versa process which we already saw. So based on this, hence we taken more than 7 to 8 classes, uh, presentations which we are already done, and a few problems, model question paper problems also discussed. So here it's a kind of revision which I am doing again with respect to the topic, whatever majorly considered on the model 3, that is impulse response properties, or the step response, or the Fourier series coefficient calculations. So with regard all this, we are going to have a problem for examination. So based on that, we will discuss few more problems again, and we'll try to revise the whatever we learned based on the module 3. So here I start with the one problem statement where we are going to check the following impulse response, whether it is memoryless, causal and stable, which we need to calculate it. So the first question under this is h of t is equal to e to the power 2t into u of t minus 1. We have exponential function along with the unit step function. So this is under continuous time signal. So continuous time signal, whether it is memoryless, causal or stable, I have to verify, but the given function is a impulse response function h of t in the continuous nature. So here the first cases is whether it is memoryless or having a memory. To identify what we need to have, I have to look for the memory is can be defined with respect to the past and the future values. If I have to remember any past or future values, then I should have some memory. So here, if t is not equal to 0, that means we are having some the value. If t is not equal to 0, here t is equal to 0, what is going to happen? H of t, whether e to the power 0 and u of t minus 1. So this value of the signal which exists, if I plot this h of t, now what is going to be observed? The signal is defined after u of t minus 1, nothing but 1 to infinity we have value for h of t. So that is nothing but, if t is not equal to 0 means, of course, I will have the value for h of t from 1 to infinity. Hence, t is not equal to 0 means t considering 1 to infinity. So that means we will have a value for h of t. So h of t is not equal to 0. So it is having some future value dependent on to the h of t. Hence, the system is having memory, or nothing but I can also say system is not memoryless. That means it is having memory. So this is how we can identify the memoryless or memory condition. So if I coming to the causality function, if I want to say it, the system is only a causal if t is less than 0. Nothing but past value, if it reaches to 0, then we can say system is causal. So that is this condition, and here t is less than 0. If suppose I taken h of t is however is 0 over here, hence system is causal. If the system is said to be a non-causal, then the depends on the system with respect to the present and the future values. So here it is having, so it is the condition here, it is a causal because h of t is not equal to, h of t is equal to 0 when t is less than 0. So if I want to look for the stability for the given h of t, so I have to take the condition for stability. It says integration minus infinity to infinity, all magnitude of h of t or h of tau d tau should equal to infinity. If you say, then it is system is unstable. So the value of h of tau, whatever the condition over to the integration of h of t, whatever you do over the interval minus infinity to infinity, it should be the value with the finite value, then only a system is stable. So here to prove this, we'll take a substitution for h of t. If I substitute for h of t, what is going to be happen? So e to the power 2 tau d tau, but I have to take the limits only 1 to infinity. However, I consider u of t minus 1. So 1 to infinity need to be considered. Take an integration for e to the power 2 tau. So e to the power 2 tau by 2 over the limits from 1 to infinity. So this will lead the value to infinity. Hence, system is unstable. So this is how I can able to prove all the properties of memory-less, causal, or stable for a given h of t function. We have one more kind of h of t we have. So e to the power minus 4 with the magnitude of t. So we can also plot the graph for h of t now. T is with the magnitude. If I remove the magnitude, we have plus or minus t value. So we have two conditions, e to the power plus 4t and e to the power minus 4t we will have. So based on that, the plot of graph is there exist from minus infinity to infinity. We have a value exponentially increasing, exponentially decreasing the plot we are going to have in h of t. So by looking this graph, I can go and I can try to identify with respect to the memoryless, causal, or stable. So memoryless condition will say if t is not equal to 0, h of t is not equal to 0 here, hence system is having a memory or system is not memoryless. If t is less than 0, h of t is not equal to 0, that is means it is having a value exist t less than 0 or t greater than 0 also and t equal to 0 also, hence system is non-causal. So to prove the stability condition, integration minus infinity to infinity h of tau d tau. So we will have the two conditions now. So we are splitting up these equations into two regions like minus infinity to 0, 0 to infinity. So minus infinity to 0, we will have magnitude of t means it is minus t. So minus minus plus, so e to the power 4 tau d tau, because h of t replaced by h of tau here. So that's why t changed to tau. So to the other region 0 to infinity, we have magnitude of t is plus t, so e to the power minus 4t 4 tau d tau. So take integration, apply the limits. After simplifying, I'm going to get half over here. So this is a finite value, hence system is stable. So this signal h of t, impulse response, is having memory. It is non-causal, it is stable. So this is how you can also able to identify. So impulse functions now is in terms of discrete nature. So how we can able to find the memoryless, causal, or stability conditions. So let us take the some problem in the discrete nature also. H of n is equal to 0.99 to the power n into u of n plus 3. So this signal, if you try to plot this signal, exists from minus 3 to infinity. So we will have the value from minus infinity minus 3 to infinity. We will have a value for h of n. That means if t is not, sorry, if not t here, it is n. So if not n is not equal to 0, we will have h of n is not equal to 0. So by this we can say system is not a memoryless or nothing, but I can also say system is having some memory. If n is less than 0, we will again we can say h of n is not equal to 0. By this we can say system is non-causal. To prove the stability condition, I'll go with the summation term now, because integration factors along with h of n or h of tau is not there here. It's h of n, so I can go with the summation factors. So summation k equal to minus infinity to infinity h of k with magnitude need to be considered. So let me take the values for this k now. So k changing from minus 3 to infinity, we will have u of n plus 3 is equal to 1. So with remaining h of n is nothing but it is 0.99 to the power k. So n changed to k, you can observe it, n changed to k here. So that's why even in the value of h of n also changed to k. So with this condition, we know this simplification in terms of summation factors. So I can take summation n equal to k to infinity. If suppose we have for alpha to the power n, then we can take alpha to the power k divided by 1 minus alpha, where alpha should be less than 1. So here we have alpha is less than 1. So k equal to minus 3 to infinity. So we have k value. This is the kind of k value what we consider over here. So we need to have 0.99 to the power minus 3 divided by 1 minus 0.99. So this is something finite value of 1 or 3. So it is less than infinity. However, this is less than infinity. So system is going to be a stable condition. Similar kind of the problems we can take it out, but I've taken one more problem over here. So in terms of combination of two signals here, combination of two impulse functions together, the h of n is equal to minus half to the power n into u of n plus 1.01 to the power n into u of n minus 1. So I have to prove again memoryless causal or stability conditions. So here, if we take n is not equal to 0, so n equal to 0, we this value is there. Okay, n equal to 0. Okay, this is dependent on at the value from 1 to infinity. So this is defined. So this is 0 to infinity, it is defined. So we are going to have, if n not equal to 0, we'll have h of n is not equal to 0. Hence system is having some memory, or you can also say system is not memoryless. So n less than 0, if you consider. So here the value exists from 0 to infinity, here value exists from 1 to infinity. So that we can say if n is less than 0, we will have h of n is equal to 0. Hence system is causal here. So if I take it to the stability condition, again in the previous problem where we considered summation factor, same thing I have to take summation k equal to minus infinity to infinity h of k with magnitude, where for the first part it is 0 to infinity. So for summation k equal to 0 to infinity, where u of n is equal to 1, the remaining factor is minus half to the power k with magnitude considered, plus second part is u of n minus 1, so 1 to infinity for k value with 1.01 to the power k with magnitude. So 1.1 1.01 means here, if you take this as alpha to the power k, so this alpha is greater than 1. That means if you take the summation till whatever the value till the infinity, the infinite sum you are going to get. So this is going to be infinite. So one factor is going to be infinite along with the other. So this may be a finite, but finite plus infinite is infinite itself. So this summation factors for h of n is reaches to infinity, hence system is unstable. So this is how very simplified we can prove it. Need not to find any finite values, corresponding any values. Simplification is not required, but justification is required over here to say this system is unstable. So moving on to the next problem is on to the step response. So we're done with the properties of the impulse response functions and its properties. You can also look forward to the theoretical concept what we discussed, how memoryless, how causality, how stabilities can be proved for the impulse response. Along with that, we have the step response conditions. It's a derivation how step response conditions can be defined. That is also important, but moreover than, we need to know about the how problems need to be solved under step response. So we can take two set of kind of functions, like one is a continuous nature and another one is discrete nature. First I'll take a continuous nature signal h of t, nothing but impulse response. For impulse response we are calculating the step response. The h of t is given here, that is e to the power minus of magnitude of t. So by this condition we can say the value of t can vary from minus infinity to infinity. So that is nothing but we can take the two sections when t is less than 0, when t greater than 0. Two cases we can consider. When t is less than 0, what we can take for this particular case, t less than 0 means I should say this t becomes minus t. So minus minus plus t, so e to the power t will be retained for h of t. But normally for step response function we have standard equation, that is always, if it is a continuous nature we need to take integration, if it is a discrete nature then I should go for summation. So continuous nature, integration required. So integration minus infinity to only defined till t, with h of tau into d tau. So h of tau when t is less than 0, I said e to the power t, nothing but e to the power tau need to be taken, minus infinity to t e to the power tau d tau. If you take the integration is of e to the power tau is e to the power tau with the limits from minus infinity to t. If you apply the limits, we will get only e to the power t when t is less than 0 for s of t. So when t is greater than or equal to 0, so what is going to be happen? So when t is greater than 0, we can take the condition now. We have, as per the standard equation, s of t is equal to integration minus infinity to t h of tau d tau, but this minus infinity to 0, we are going to have a value as minus of minus plus e to the power tau d tau plus for the upper part 0 to t, we will have a value e to the power minus tau d tau. So the first section, however, we calculated, but the limits now it's changed minus infinity to 0. For the second part, we will have e to the power minus tau by minus 1 with the limits 0 to t. Apply the limits. After simplification, I'll get s of t is equal to 2 minus e to the power minus t when t is greater than or equal to 0. So s of t, that is step response for a given h of t. Now we will have e to the power t when t is less than 0, and when t is greater than or equal to 0, we'll have s of t is equal to 2 minus e to the power minus t. So this is how we find the step response for a given impulse response function. Moving on to the next one is again the under continuous nature h of t. So given is under h of t is e to the power minus t into u of t convoluted with the delta t minus 2. So the question h of t now little bit complicated. So the convolution between the two terms, that is what h of t. So for that I have to take step response. So what we can do over here, first we can simplify h of t in terms of convolution function into a single function. So as we know that this given function is looking like a term x of t convoluted with something delta function. So any term x of t is convoluted with the delta function means what we can take this delta function as you look like delta t minus t naught with the time shifted delta. So that time shifted value we can put it into the x of t. So x of t convoluted with delta t minus t naught, nothing but this is simplified as x of t minus t naught. So time shifted function of delta will be shifted into the x of t, that's it. So x of t minus t naught. This is one of the properties, convolution property with respect to the the time shifted convolution with respect to the delta function, where we can directly taken this as a standard condition to simplify this factor. So e to the power minus t into u of t is x of t convoluted with the delta t minus t naught, that is delta t minus 2 here, t naught is 2. So what we going to have x of t minus t naught means e to the power minus t minus 2 into u of t minus 2. So we see simplified h of t now as e to the power minus t minus 2 into u of t minus 2. So for this h of t, I have to calculate step response. So we know the step response equation. Previous I just considered integration minus infinity to t h of tau d tau. Substitute for h of tau now is in terms of exponential and the unit step function. So this unit step function is defined from only 2 to infinity is required. So what we can do, if u of tau minus 2 replaced into 1 means I have to take the range from 2 to t with e to the power minus tau minus 2 d tau. So if you apply the integration, then apply the limits, after simplification I'll get s of t is equal to 1 minus e to the power minus t minus 2 when this is only defined from 2 to infinity, only possible for t greater than or equal to 2. If t is less than 2, we are going to have 0 because we are not defined when t is less than 2. The h of t is not defined, hence we cannot also able to calculate s of t. S of t equal to 0 when t is less than 2. So this is how we can find the step response for a given kind of question here with convolution kind of functions. One more problem I just taken for step response in the discrete nature. So this is also we discussed the same similar kind of problems we discussed, but I just revised this topic over here again. So h of n is equal to minus 1 to the power n with the sum of the unit step function given as u of n plus 2 minus u of n plus n minus 3. If I able to sketch this x of n, so only if you define this u of n plus 2 defined from minus 2 to infinity, u of n minus 3 is defined from 3 to infinity. If you subtract these two, only value exists from minus 2 to till 3, not exactly at 3, till 3. So minus 2 to till 3. So this is multiplied with minus 1 to the power n. So when n equal to minus 2, so when n equal to minus 2, what is going to be happen? Minus 1 to the power minus 2, that means 1 by minus 1 whole square, that means plus 1. So plus 1 will be there at minus 2. When n equal to minus 1, we will have a value. When n equal to minus 1, what is going to be happen? Minus 1 itself. When n is equal to 0, so we'll have 1. When n equal to minus 1, we'll have minus 1. When n equal to 2, we'll have plus 1. When n equal to 3, this is 0. 0 into anything is 0 itself. When n is minus 3, this is 0. 0 into anything is 0 itself. When n equal to more than 3, less than minus 3, we will have 0 into minus 1 to the power any values will be 0 itself. So value is defined from minus 2 to till exact at till 3 till 2. So this for this I just have to do the step response function. I have to calculate s of n, which is nothing but the running sum of the given equation k equal to minus infinity to n with h of k. So running sum I have to calculate. So running from sum from minus infinity to n value which we need to do. So minus infinity to till minus 3 as per the observation for n. When n value minus infinity to till 3, no values are there for h of n. So running sum over here till here, s of n is equal to 0. When it reaches to n equal to minus 2, so all these values till minus 3 is 0, but add to minus 2 will have 1. So all the summation of this 0, 0, 0 plus 0 plus 0 plus last at I have 1 here. So 1. So we will have when n equal to minus 2, we have running sum from minus infinity to till minus 2, we will have 1. So when n equal to minus 2, we have s of n is equal to 1. So when n is equal to minus 1, what is going to be happen? 0 plus 0 plus 0 plus 0 till here 0. So 1 plus minus 1. So at n equal to minus 1, we have s of n is equal to 0. When n equal to 0, running sum from minus infinity to till 0, 0, 0, 0, 0 added along with 1 minus 1 plus 1 added. So what is the answer? We will have 1 when n equal to 0. So when n equal to 1, what is going to be happen? Running sum 0, 0, 0, 0, 0 added, 1 minus 1 plus 1 minus 1 added. So what is going to be happen? 0 will be there when n equal to 1. So when n equal to 2, what is going to be happen? So this minus this, all are zeros except 1. So 1 is remaining when n equal to 2. So when n equal to 3, so this will continue now after from 2. This is continuously s of n is equal to 1 when n is greater than or equal to 2. So this is how we can observe the value for s of n is equal to 1 at minus 2, at 0, at more than 2. So this is what the plot we can take it for s of n for a given impulse function in terms of h of n given in this order. So this is how we can calculate the step response of a signal. Coming to the next problem is the complex Fourier series coefficient for a given any periodic waveform x of t is shown in the figure. So here this signal is given in terms of triangular function which is repeated over every time interval t equal to 1. So by the observation what we can observe, the fundamental period over here t equal to 1. So omega naught what I can consider 2 pi by t is equal to 2 pi itself. So expression for x of t is given by expression for this signal over the one fundamental period t equal to 1, 0 to 1 I will consider. So at 0 to 1, one fundamental period, the equation x of t in terms of it is equal to t. So I have to find here the complex Fourier series coefficient, that is nothing but capital X of k I have to calculate, which is nothing but 1 by t over the integration over one fundamental period with x of t into e to the power minus jk omega naught t dt. Here omega naught is equal to 2 pi for the problem. So I can substitute t is equal to 1. So x of k is equal to t 1 by 1 is 1 itself. Integration one fundamental period I'll take on 0 to 1. So 0 to 1 with the x of t you can substitute t e to the power minus jk with omega naught is 2 pi t dt. So we have a two term multiplication here. So first term as it is, integration of second term minus, first I will take integration for the second term, differentiation of first term, the whole term is integrated again. So differentiation of t is equal to 1. So double integration for exponential will be this. So this is defined 0 to 1 interval. So apply the limits, simplify it, I'll get x of k is equal to e to the power minus jk 2 pi minus jk 2 pi. So this is what I can get. This is not possible when k equal to 0. So when k equal to 0, what is going to happen? Under integration e to the power minus jk 2 pi into 0. So e to the power something is 0 is equal to 1. So integration 0 to 1 with the t. So dt is only remaining when k equal to 0. So what is going to happen for x of k is equal to half. So x of k we have two set of values. When k equal to 0 is half. When k is not equal to 0, we'll have this equation which we can obtain for x of k. So this is the Fourier series coefficient value. So you can also plot the graph in terms of magnitude and phase spectra. Also here I just not done that particular plotting of magnitude and phase spectra. So you can try it in your home. You can take different set of variety of problem under Fourier series coefficient also. Please try to solve more problems under these particular category. Very important, all these kind of problem varieties are solved under step response or the properties of impulse responses or Fourier series coefficient calculations. The vice versa can also be done. So these are major problems you can expect for examinations. So keep learning with all these kind of problems or theoretical concept and the properties of a Fourier series coefficient also important. So look into the all the concepts under this particular module, revise it. If you have any doubt, please contact me, and have keep learning all the concept. Thank you.